Hello and welcome back to another deep dive. Today we are looking at something so common, so integrated into our daily lives that we barely even notice it until it fails, of course. It is probably sitting in the remote control on your coffee table or maybe inside the very device you're using to listen to this right now.
I mean, it's the silent engine of the portable world, isn't it? Without it, we would still be, tied to wall sockets for absolutely everything.
But before we reveal the topic, though I think you've probably guessed it, I have a bit of a mystery for you. It's a scenario every single one of our listeners has faced. You're watching TV, you go to change the channel, and nothing. The remote stops working.
Yes. And then you press the button harder.
Exactly, which makes zero logical sense, but we all do it. You take the battery cover off, you spin the batteries around, and maybe, just maybe, you get one last channel change out of it. Finally, you give up and you say, the batteries are dead.
The universal sign of defeat.
Right. But here's the question that's always bothered me. When we say a battery is dead, what does that actually mean, physically? Is it empty? Is the voltage inside strictly zero?
That's a brilliant question.
Mm-hmm.
And it's a very dangerous assumption for a science student to make. If you actually took a voltmeter and measured that dead AA battery from your remote, you'd find something pretty surprising.
Oh.
It usually still reads about 1.0 to 1.2 volts.
Wait, hold on. A fresh alkaline battery, that's 1.5 volts, right?
Correct.
So if it's still at 1.2 volts, it's almost 80% of its voltage. Why on earth do we call it dead? Why doesn't the remote just, I don't know, work a bit slower?
And that is the core mystery we need to solve today. See, it's not that the voltage is zero, it's that the battery has lost its ability to, push that energy out when you ask for it. It's a problem of what we call internal resistance. The battery isn't empty, it's clogged.
Clogged. Okay, I like that image. I need to understand the science behind it, though. So today we are diving into Unit 2, Electrochemistry, and we are tackling batteries.
Our mission is to look inside that little metal can. We need to understand how we store chemical energy, how we make it portable, and exactly what is happening chemically when it dies.
And for our student listeners, the ones preparing for their Class 12 board exams, why is this specific topic so critical?
Because batteries are really the most practical, everyday application of redox reactions. In the exams, you'll definitely be tested on the difference between primary and secondary cells, the discharge equations, and crucially, you need to be rock solid on the definitions of anode and cathode, because in batteries, they can be a bit tricky.
Okay, let's start at the very, very beginning. Forget the complex diagrams for a moment.
Yeah.
At the absolute simplest level, what is a battery?
At the simplest level, a battery is a canned, spontaneous redox reaction.
A canned reaction. Okay.
Think about it. There are chemical reactions that naturally want to happen. In thermodynamics terms, they have a negative Gibbs free energy. They're just desperate to react and release energy. But inside a battery, we've separated the chemicals. We have, in effect, hit the pause button on the reaction.
So it's a reaction just waiting for permission to start.
Exactly. The chemicals are stuck in this high-energy, incomplete state. They want to exchange electrons, but we've put a barrier between them. The moment you put that battery into a flashlight and flip the switch, you're completing the circuit. You're unpausing the movie. You're giving the electrons a path to flow from one side to the other.
And that flow of electrons, that's the electricity.
Yes. And we should be very precise here about the mechanism. What's really happening is that electrons are flowing from the anode to the cathode, but through the external circuit. That's your wire, your light bulb.
Okay, so electrons go around the outside.
But you can't just move negative charge one way without balancing it, right? So at the same time, ions have to flow through the internal electrolyte inside the battery to balance the charge.
Electrons outside, ions inside. Okay. Now, I have to clear up something I think a lot of students get confused about. We use the word battery for everything, but in the textbook, we also see the word cell. Are they the same thing?
This is a classic misunderstanding trigger. Strictly speaking, no. A cell, or a galvanic cell, is the basic unit. It creates a certain voltage based on its chemistry. A battery, technically, is a collection of cells connected in series.
So a battery is just a stack of cells.
Historically, yes. Think about a standard 12-volt car battery.
Mm-hmm.
If you were to open it up, which please do not do, you would find it's actually 6 individual 2-volt cells all connected in a chain, 2 plus 2 plus 2.
Yeah.
6 times gives you 12 volts.
So the rule is you connect cells in series and their voltages add up.
Precisely. Even a 9-volt battery, the rectangular one. Inside that little box, there are 6 tiny 1.5-volt cells stacked right on top of each other.
That is fascinating. So when I put 2 AA batteries in my remote, I'm kind of building a 3-volt battery pack right there.
You are. You're acting as the battery engineer.
Okay, I want to visualize this stored energy thing better. Chemistry can get very abstract with all the ions and electrons. Do we have a good analogy for this?
The best analogy for a primary battery, like an alkaline cell, is the compressed spring.
Okay, walk me through it.
Imagine a really strong metal spring. When you buy a fresh battery, it's like that spring has been squeezed down, compressed tightly, and locked in a box. It has a lot of potential energy. It's pushing against the lid, just ready to snap back.
So the potential in the spring is like the chemical potential in the battery. Makes sense.
And when you turn on your device, it's like you're unlocking that box and letting the spring slowly expand. As it expands, it pushes gears, it moves things. It does work. That's the battery pushing electrons.
And a dead battery.
A dead battery is a fully released spring. Now, here's the key part. Has the metal of the spring disappeared?
No, of course not. The spring is still there. It's just loose, relaxed.
Right. The matter is still there, but the potential is gone. The reactants have been consumed and they've turned into products. They've reached equilibrium. There's no more drive to push electrons.
That explains why the dead battery still feels heavy. The chemicals didn't vanish, they just changed form.
Precisely. And there's one more analogy which is really critical for understanding voltage versus capacity. Think of a water tank on a hill.
I remember this one from physics class.
It's a classic for a reason. The height of the hill, that represents the voltage. A higher hill means the water has more pressure, more potential to do work when it falls.
And the size of the tank itself?
The size of the tank is the capacity, basically how much charge it holds.
Okay, let me test this. A tiny little AAA battery and a big chunky D-cell battery. Both say 1.5 volts on the label.
Yes, they do.
So that means they're sitting on hills of the same height.
Correct. Their pressure, or voltage, is identical because their chemistry is identical.
But the D-cell is a much, much bigger tank.
Exactly. It has more reactants inside, more zinc, more manganese dioxide.
Yeah.
So while it pushes with the same force, it can keep pushing for a much longer time.
Yeah.
Students often make the mistake of thinking a bigger battery has more voltage. It usually doesn't. It just has more life.
That is such a helpful distinction. Voltage is the intensity, capacity is the duration.
You've got it.
Okay, let's move from analogies to the actual chemistry. I want to do a mental movie. I want to actually see what's happening inside that metal can when I'm using it.
Let's do it. I want you to close your eyes. Picture a standard alkaline AA battery, the kind you buy in any shop. Now, imagine we slice it right down the middle, lengthwise.
Okay, I'm picturing the cross-section.
It's not just a bucket of chemicals, it's highly structured. First, look at the outer casing, that shiny metal container. It isn't just a wrapper, that is the anode. It's made of zinc metal.
Wait, the container itself is the fuel?
Yes. The zinc can is the negative terminal. It's the anode. Now look right at the center. There's a black rod running down the middle. That's a graphite or carbon rod. That acts as the current collector for the positive terminal, the cathode.
Okay, so zinc wall on the outside, carbon rod in the middle. What's in the space between them?
That's filled with a thick most paste. This is your electrolyte. In an alkaline battery, it's a mixture of potassium hydroxide, that's the alkali, and manganese dioxide.
Okay, I've got the setup. The zinc can, carbon rod, electrolyte paste. Now, I flip the switch on my flashlight. Action.
Action. The reaction begins. The zinc atoms in that outer can, they start to oxidize. The crucial equation is xenon right arrow, Zn2 plus 2E.
So the metal atoms are splitting.
The zinc atoms are giving up 2 electrons each, and dissolving into the paste is zinc ions. If you can see this with microscopic eyes, that shiny, solid metal wall is actually getting thinner. It's literally being eaten away.
Oh, that sounds destructive. The battery is consuming its own container.
It is. That's where the electrons come from. They rush out of that dissolving zinc, travel through the wire to light up your bulb, and then they return into the carbon rod at the center.
And the paste, what's happening in there?
The paste is changing too. The manganese dioxide is accepting those returning electrons and reacting with the electrolyte. The moist, active paste is slowly turning into a different chemical structure. It becomes dry, hard, and, well, crowded with reaction products.
So a fresh battery has a solid wall and moist paste. A dead battery has a thin, pitted wall and a dry, crusty interior.
Exactly. And this brings us right back to your first question about the dead battery and the 1.2 volts.
Right, the clogged battery.
As that paste turns into this dry, crowded mess of products, it becomes very, very difficult for the ions to move through it. In physics terms, the internal resistance of the battery skyrockets.
Okay, so internal resistance is the opposition to the flow inside the battery.
Right. Think of it like a hallway. In a new battery, the hallway is empty. Ions can run back and forth easily. In a dead battery, that hallway is packed with people. Those are the reaction products.
So even if there is still a voltage, even if there's still a push, no one can move through the crowd?
Exactly. The voltmeter reads 1.2 volts because there's still a chemical potential difference. But the moment you try to draw a current from it, the moment you try to run the remote, that voltage collapses. The ions just can't move fast enough to sustain it. The push is there, but the flow is blocked.
That makes perfect sense. So dead doesn't mean empty, it just means the internal resistance is too high to be useful.
And this leads to another thing you might have noticed. Have you ever taken a dead battery out, let it sit for an hour, put it back in, and it works for another minute or two?
Yes, all the time. It's like it rested and got some energy back.
It didn't get energy back. It just allowed the ions in that crowded hallway to slowly spread out a bit while the current was off. It lowers the resistance, but only temporarily. As soon as you use it, the jam forms again.
That is such a great practical insight. Okay, speaking of practical things, what about heat? Why does my phone, or a powerful toy, get warm when I use it?
That, again, is the internal resistance at work. We know from thermodynamics that no energy conversion is 100% efficient. No. Nature always charges a tax.
The entropy tax.
So when you force current through that electrolyte paste, the friction of the ions moving generates heat. If you're using a high-drain device like a digital camera or a drone, you're forcing a lot of current through very, very quickly.
You're making everyone sprint down that hallway.
And that friction creates a lot of heat. A remote control, on the other hand, it just sips power. The movement is so slow that the heat dissipates before you can even feel it.
Now, I have to ask about the big technology difference here. We've been talking about zinc cans dissolving. That sounds, well, permanent. You can't undissolve a metal can.
Correct.
Yeah.
So reversible.
But my laptop and my phone use lithium-ion batteries. I charge them every single day. How is that different?
This is the key distinction between primary batteries, which are non-rechargeable, and secondary batteries, which are rechargeable.
Primary is one-time use. Secondary is reusable.
In that zinc alkaline battery, the reaction is, as you said, irreversible. Once the zinc becomes zinc ions and mixes into the paste, you can't just force it back into a solid metal shape by applying electricity. It's like trying to unbake a cake. The structure's just gone.
So how does lithium-ion perform this magic trick?
Lithium-ion batteries work on a completely different principle called intercalation.
Intercalation. Okay, that's a big word.
It sounds complex, but the idea is actually quite simple. Instead of dissolving the structure of the electrode, the lithium ions just move into and out of tiny spaces within the electrode material.
Give me a visual.
Imagine a bookshelf. The lithium ions are like books. When you use the battery, when you discharge it, you're just taking books off the anode shelf and moving them to the cathode shelf. The shells themselves, the structure, they don't break or dissolve. They just get filled or emptied.
And charging it.
Charging is just putting all the books back on the original shelf. And because the structure, the bookshelf, stays intact, you can do this back and forth thousands of times. Some people call it rocking chair technology. The ions just rock back and forth.
That's brilliant. So alkaline consumes its structure, lithium-ion just borrows space in its structure.
Precisely.
One last mystery before we summarize for the exams. Shelf life. If I buy a battery and I put it in a drawer for 5 years, it's basically new, right? It hasn't done any work.
Unfortunately, no. Batteries suffer from something called self-discharge.
Meaning they lose energy even when they're not connected to anything.
Yes. The separator between the anode and cathode isn't perfect. Even without a wire, there are tiny, microscopic parasitic reactions happening. The chemicals are just slowly reacting with each other at a very, very low rate.
So the compressed spring is slowly rusting or losing its tension even while the box is locked?
That's a great way to picture it. A battery from 2018, even in a sealed package, will have noticeably less capacity than a fresh one because those internal reactions have been eating away at the fuel for years.
So, moral of the story, check the expiration dates, even on new packs.
Absolutely.
All right, we have covered a huge amount of ground here. For our Class 12 students, let's lock this down. We need the exam-safe clarity lines, the points you just cannot afford to mess up.
Okay, let's take these one by one. Get ready to note these down.
Clarity line number 1.
Point 1. A battery is one or more galvanic cells connected in series. Remember, it's the series connection that adds up the voltage. That's how you get from 1.5 volts to 9 volts.
Got it. Series adds voltage. Line number 2.
This is the most critical one. Point 2. In a battery, which is a galvanic cell, the negative terminal is the anode.
Negative is anode.
And consequently, the positive terminal is the cathode.
Why is that so confusing for students?
Because in electrolytic cells, where you use electricity to drive a reaction, it's the other way around. But for batteries, which produce electricity, oxidation happens at the anode, releasing electrons, which makes it negative. You must keep this clear.
Anode is negative for batteries. Got it. Line number 3.
Point 3. Voltage depends on chemistry. Capacity depends on size.
Just like our water tank analogy.
Exactly. A big D cell and a small AAA cell have the same chemicals, so they have the same voltage. The big cell just has more reactance, so it has more capacity. Don't confuse the two.
And finally, line number 4.
Point 4. Alkaline batteries are irreversible. They are primary cells. Lithium-ion batteries are reversible. They are secondary cells.
And that key word for lithium-ion was?
Intercalation. If you can use that word in your exam to explain why the structure doesn't break down, you will definitely score top marks on that question.
Perfect. Okay, let's bring this all home. A quick summary.
Okay. The core idea. A battery is just a canned spontaneous redox reaction. It's stored chemical potential energy.
The mechanism.
Electrons flow from anode to cathode on the outside. Ions flow through the electrolyte on the inside.
The visual to remember.
Picture the zinc canister physically dissolving to release electrons, and think of the internal resistance building up like a crowded hallway, which is why a dead battery isn't really empty.
And the golden rule for exams?
Anode is negative.
Yeah.
It's the source of the electrons.
I feel so much clearer about my remote control problems now. It's not just dead, it's chemically exhausted and internally resistant.
It has fought a good chemical fight.
Before we sign off, I just want to leave our listeners with one final thought. We accept that batteries die. We accept that the zinc dissolves. But look at the progress we made from alkaline to lithium-ion. We went from literally destroying the house to just, moving books around on a shelf.
It was a massive leap for sure.
Well, the holy grail of battery research right now is to make that process perfect. Imagine a battery where the reaction is 100% reversible, with zero degradation, zero side reactions. A battery you buy once, and it just lasts.
We're not there yet, but thermodynamics doesn't say it's impossible. It's just a very, very difficult engineering problem.
And that is exactly why we need smart students studying electrochemistry. The next breakthrough could be yours. Thanks for listening to this deep dive.
Stay charged.